Okay, so welcome back, everybody, to the fourth episode of the Math and Physics podcast. So I'm your host, Parker.
And I am Ray, and today we have a very special guest, Dr. Pekka Sinervo from U of T. Mr. Sinervo?
Hi there.
Hi. Okay. Okay. So today we're gonna be just having a few questions for Dr. Sinervo, just understanding how he got to where he is today. I can just give like a small history of how I know Dr. Sinervo. So he was my professor of one of my seminar classes in the first year of U of T, 199. That would be the dark matter course. So we were talking about dark matter, dark energy, a lot of interesting things in the universe, and yeah, so that's where I know Dr. Sinervo from. So that's pretty much the background behind how we know each other. So yeah, so we can just dive into it. Parker?
Awesome. Yeah, you can go ahead with your first question.
Okay, so my first question to Dr. Sinervo would just be how did you get into the field of physics? Like, when did you know that you liked it?
It's hard to know exactly the very moment that this actually took place. Uh,
Mm-hmm.
Growing up, I was interested in maths and physics and computer science. I did a lot of things that, involved just sort of figuring out how to understand how things just basically worked. I turned out
Mm-hmm.
became the sort of mechanic in the family. Uh, but as I went through high school, they also appreciated that I did math really well. By the time I got to university, I took a math and physics program, not quite sure which direction I really wanted to go. And by the middle of my second year, I realized that I really liked working in the lab and
Mm.
that the trying to get do measurements and understand things the that happen around me the was what really turned me on, and so that's what actually led me to decide that physics was really the right sort of career. And the so I completed the math and physics program, but then went on to focus on experimental physics.
Oh yeah, so you mainly focused on the experimental part, right?
Yeah,
Which is yeah.
experiment is not just about going and working in the lab and doing measurements, but it's also the analyzing the data and understanding, what are the possible ways of the taking the information and saying something about how what the underlying system that you're actually studying. So I do a lot of what you might consider are sort of mathematically oriented things. I do a lot of
Mm-hmm.
detailed statistical analysis and the model building, spend a lot of time on computers, building up computer models and simulations, the, and then doing measurements that I can compare directly with theoretical predictions of the phenomena. So it's a combination of things that are sort of in the lab and measurements and figuring out uncertainties, and then doing the interpretation and working to understand what it all means.
Okay. Okay, that's actually really interesting. That's really
Yeah,
cool that in the experimental side of things.
yeah. When I was in high school, I actually had like a similar thought process. I was taking like in grade 12, I was taking math and physics, and I couldn't decide whether I'd want to go strictly into math or do math and physics at U of T. And so I ended up just going into like choosing physics, going into math and physics, and then obviously I loved my program. I loved my first year, so I'm gonna stick to physics. But I also really love math, which actually plays a huge role in physics.
Mm-hmm. Interesting story about me actually. I funny story. I actually hated math when I started loving physics. I was very very young, and I just loved how the universe worked, and I absolutely detested the math. Like wherever it was, I would just not care about it. I would just skip that part. For example, if I was watching a video on physics, I would literally skip the math part because I would hate math that much. And this was in grade 6 and 7. And then I moved to Canada, And that's actually when I started really enjoying math a lot more. And then I continued on. So a little different story on how I got onto the path, but yeah.
Yeah, the issue of, how maths actually and physics interact is something that is had the degree of controversy be associated with it, or at least
Hmm.
different views. There are some people who actually believe that our world is fundamentally mathematical, and that one actually can describe everything with some form of a mathematical
Using math.
theory or description. Uh, there are
Yeah.
others who actually are somewhat more skeptical that, in fact, the world is fundamentally, mathematical. But rather see it as one of the tools, a pretty good tool, but only one of the tools, for figuring out how the world works around us. Um, a very good example of this is that if you go and look at the biological sciences, um, now this is not
Hmm.
physics, but they actually, it's a science, and you're doing measurements, and you're using, you are using math, but it's much less important in a certain sense. Observation and cataloging and understanding species, doesn't require high math. Nonetheless, it is a science.
Yeah.
So, there and there are
That's
parts
true.
of physics that actually have not been soluble, or we don't have a theory that we actually can claim really describe the phenomena. We have things that are approximations, and in certain cases, we actually don't even have a very good, even approximation to understand what's going on from a mathematical point of view. A very simple example is, you look at complex phenomena like the sand on a beach. The patterns that are formed by the
Hmm.
wind on a beach, they actually are very difficult to describe mathematically.
Yeah.
Hmm.
That's actually really a really interesting example.
Yeah, there are a lot of.
Yeah.
It's like
Oh, no, I was
oh,
just
go
going to say
ahead.
there's lots of phenomena like that. How cream or milk actually gets diffuses into a coffee cup. Yeah, that's also a system that we've not been able to come up with a really good theory to describe.
Well, that's actually pretty sad if you think about it, that we have theories of the universe and we don't even know how cream mixes with coffee.
Yeah, so I'm actually on the side of the skeptics who aren't, I'm not convinced yet that in fact mathematics is the only language you can use to describe our world.
Hmm.
Oh wow.
Wow, that's big
That's
stance.
yeah, that's pretty cool. So, you got your bachelor's degree at the University of Toronto, and then you moved to Stanford. So can you just talk about your post-secondary career, or yeah, your post-secondary path?
Well, so when I finished, or I was finishing my undergraduate degree, I started looking around for departments and universities where I'd actually be able to do the kind of science I wanted, which I'd already decided I wanted to understand particle physics
Hmm.
better. So I had a handful of places that had a very strong particle physics effort, and the ones that were most attractive were the universities that had access to the sorts of facilities you need to do particle physics experiments. The
Right,
Stanford has a 3 kilometer long linear accelerator, an electron accelerator, and or it actually operates it for the Department of Energy. So I really was a graduate student at that lab. And so, you were, you could actually do the experiments at the lab. I didn't have to travel anywhere. It was just all there. So that was one of the things that made Stanford attractive. And the other thing was that there were some really great people. Uh, I think I count 3 Nobel laureates, just in my
Wow.
field of physics,
oh
at the
wow.
lab. So it was a fairly, interesting place to be, especially in the 1980s when I was there.
And
Yeah.
this is going to be slightly actually not really an objective question, but just an interesting question. Was it hard to get into Stanford? Like, did you need a 4.0 or some crazy GPA like that? Or was it just like a bunch of entrance essays or some research that you had to do to get in? Like, how would you get into a prestigious school such as Stanford for your PhD?
Well, so uh, graduate schools look at people from many different perspectives, and so
Mhm.
the information that they have your transcript, and so a strong transcript is helpful. You write the graduate record exam, the GREs, and so that's information that's used. Letters of reference from people that you've worked with as an undergraduate are quite important because they probably give the best, most insight into what the potential the student has. The and then in many cases you actually get you have some interaction with the student or the when they're actually applying or looking at different programs. The so all of that gets put together. It's a competitive place. So, I think we had a
Mhm.
class of 20 and there were about 400 applicants. Um,
Wow. Okay.
and so I did have a strong transcript. It was essentially a 4.0. I did really well on my GREs. I had good letters, I know. I don't know what they said, but I had actually been working for several years as a research assistant. So, my package was, I think, reasonably strong. The
Wow.
Yeah.
Okay. And did you get your PA? Like, did you do your master's and PhD at Stanford,
it's just
or did you?
in the US, it's actually pretty common, and now it's actually getting more common in Canada to go and do a straight PhD program where
Oh,
Oh,
I didn't know
wow.
that.
Wait. So no masters?
so no master's degree. It's essentially
Oh.
structured so that the in the PhD program, within the first 2 years, you end up having to go through write a qualifying exam, yeah, or some sort of an
Oh.
examination like that. And if you fail that exam, or then you can actually often will be awarded a master's degree because you've completed all the coursework, and that
Okay.
would actually be equivalent to the work expected in the master's program. The but
And
you sort of go through directly into a PhD program, and and that's
Oh, wow.
that's sort of what happens right now at U of T. About two-thirds of our incoming students go directly into the what we call the direct entry PhD.
Wow.
and
That's.
so how many years did you spend at Stanford?
So I was there for not quite six. About I started there in September and left about 5 and 3/4 years later. The sort of in the May June the period.
And what did you write your thesis on, if you don't
Ah,
mind me asking?
no, I don't mind. It's um, when I went there, the one of the things that we were actually trying to understand was the behavior of quarks and what were the forces that caused quarks to interact and come together to form the particles that we actually see.
Hmm.
And one class or group of particles are those that are formed from a quark and an antiquark. They're a family of particles called mesons. Uh, and these mesons, they come in different energy states. So you have a ground state of a meson, the state that is most stable. But then you have excited states where the quarks and antiquark are they're behaving differently. They are in a higher rotational state, or they're actually acting like they're bouncing off of each other. So they're in a sort of a vibrational state. Uh, and by looking at those energy levels, you actually learn about what are the forces that cause that rotation and that those radial, the excitations. And so my work was actually uh, discovering a number of those higher energy states. And from that,
Wow.
being able to then talk about what the forces are between these quarks. Um, so the title of my dissertation is a little bit gobbledygook. It's, a study of the strange meson spectrum, the in K minus proton interactions. at 11 giga electron volts. You know,
Okay, I'm not gonna lie. I do not think Parker and I fully understood that, but I think we can appreciate it for what it is. It's
Yeah.
very, very commendable. I'll give
I
you
mean,
that.
hopefully one day we will be
One
on the
day,
level to understand that. Yeah.
not yet, not yet. Okay, so just continuing. Just a quick question: were there any like setbacks or some things that you didn't expect on your journey to where you are today? Like, were there any big moments, big regrets in obviously professional in your professional career that you had?
yeah. There was
Okay.
probably one. The When I was a postdoc and then my first year as an assistant professor, I was working at a experiment at a lab called Fermilab near
Oh,
Chicago, where we were colliding
you
proton
worked
and
at
antiproton
Fermilab.
together.
Wow.
Yeah.
Okay.
And
Okay.
so I was working there, but we were at the same time, in the US, the decision was made to build a much larger
Hmm.
proton collider called the Superconducting Super Collider, which was construction of it started around 1988, and I was actually part of one of the collaborations of scientists that was proposing one of the big detectors to be built
Wow.
there, and that we would use to study the proton high energy proton collisions. So we worked on that real hard. We had already designed the detector largely. I was working on designing and building the electronics that would actually read out part of the detector. Um, and so that was going along. We had gotten a lot of funding to do that and had a group together already at Toronto now. And then in 1993, the US Congress
Oh
canceled
Oh.
the
no.
project. So that was 5 years of work
Oh,
Oh
down the
no.
drain.
wow. Okay.
The
Quite a big setback in the career.
uh, yeah, yeah. So at the same time, we've been working at Fermilab, and so it wasn't like it was all of 5 years gone. But a significant part of my 5 years of effort was associated with the SSC. And more importantly, perhaps, it was what I thought to be the future of where I was going to go. So I needed to reassess what the options were, and ultimately decided to work on an experiment that would take place at the Large
Mm.
Hadron Collider in Geneva, Switzerland.
Wow. So that was a
Yeah,
big
and so
career change.
it was a pretty big, well, career change may be too strong, but certainly
Sorry,
changing
sorry. Yeah, yeah,
direction
sorry.
of that
Not
whole
career
career.
change. That was the wrong word, but
Yeah,
like
right.
change in, yeah,
Yeah.
yeah, sorry. I understand. I understand.
And it worked out. We thought we'd actually start taking data by around 2007,
Hmm.
2008, and we really only started to get data around 2011, 2012. But in the first few years, we discovered the Higgs boson. And have now been searching for things like dark matter and other sorts of phenomena that we think should be occurring in these high energy proton collisions. So it's been okay. In fact, I've been very pleased at how things have developed. But the demise of the SSC was such that we could have been doing the science 15 years earlier.
Mm,
Yeah,
okay.
so can you explain for us and the audience what the Higgs boson is and how you and your team came about its discovery?
So the Higgs boson, some people, it's been given the name, and it's the somewhat facetious, but been called the God
Hmm.
particle, and its role is that uh, it is a particle that interacts with all of the other particles that have mass. And the interaction of the Higgs boson with these particles, like quarks and electrons and cousins of electrons, are what actually end up giving these particles their mass. So if the Higgs boson didn't exist, there would be no way for these particles to be massive. And so our world would look completely different.
Hmm.
The fact that it actually interacts then with all particles that are massive means that if you've ever read the Tolkien's The Lord of the Rings, there's one ring that
Mm-hmm.
rules,
Yeah.
and the Higgs boson
Is that
is
one
that
ring?
one ring.
Okay.
Wow.
The
Well put. Well put.
so it is so that's what made it important because it had been predicted. The In the theory that we had put together to describe all the various forces that we knew about, but it hadn't been
So
observed,
it was kind of like a missing
and so
piece.
it was a missing piece. And if it didn't exist, then the theory we had was just broken. It was not
Oh.
correct. So it was a real strong test of what we call the standard model,
Hmm.
the name that we give to the theory
And
that we use to describe.
and I'm assuming that this was all done in the LHC, right?
That's
Yeah,
right.
and so just a question that I've always wanted to ask someone that worked at the LHC. How was it like working there? Because I've been there once when it was working, like it was currently on, so unfortunately I couldn't observe the LHC, but I was on top and it was just a beautiful experience just sitting there watching people looking at the data. So I just want to ask you from a
Mhm.
first person view, right? Like how was it working at the LHC?
Well, so the detector that we build are
Okay,
underground,
yeah.
and they're in large caverns, and it takes a ton of engineering and design to be able to ensure that what you actually, when you get down there and the equipment that you've built actually gets installed. Um, it's a huge amount of planning and the people looking over the plan and reviewing things before you even start. Um, so working there, building the detectors and installing them was really thrilling because you finally started seeing this big detector start coming together from literally all corners of the world, people bringing components that they had built. And then some of the components that were very large having been built right on the Cern site. Um, so that was actually a lot of fun. From an experimental science point of view, you really were able to see how at least we're starting to get the detector operating. And so once you got the detector going, and that meant being down in the pit for a long time. I think it took us close to a decade to actually build the detector. But once you started turning it on and you started looking at the data coming out of it, then the challenge turned to figuring out what this data means. Is the detector really working? How well is it
Right.
working? Calibrating it and all that other stuff, which is also exciting, but in a different way, because now you're actually beginning to see the detector come to life.
Yeah.
The And then starting to run with proton collisions was another, exciting time when we could actually finally see the detector doing what it was designed to do. The and then the search began. Then we started looking at collisions. Then you have to realize we looked at a gazillion collisions. We looked at trillions of collisions. The Before we actually had uh, enough collision that had evidence of a Higgs boson that we could claim that we've observed something new.
Yeah, so I don't know much about the LHC, so this might seem like a silly question, but like how do you isolate like singular particles and then make them crash into each other in the collider?
So it's actually pretty easy, relatively speaking, to actually isolate protons. Protons are the nucleus of a hydrogen atom. So if you just took hydrogen gas, which you can purify and get, so you can just have a bottle of hydrogen gas,
Yeah.
and you take it out, you can actually strip the electrons off it pretty easily in an electromagnetic field, and then you just have protons.
Wow.
And now you can use the electromagnetic fields to actually begin accelerating them. And you then have magnets which focus these accelerated protons into a bunch, into a beam and you keep on accelerating them.
Okay.
And so that's how you actually make a beam of protons.
So you
It's
don't
pretty
actually,
straightforward.
yeah, so you don't actually just do one proton. You do like a whole bunch into a stream.
exactly.
Okay, yeah.
And the number of protons we put into a bunch is around 10 to the 11, right? So about 100 billion protons
Yeah.
are
Wow.
in a single bunch. And we have about 2,000 bunches in the collider at one time. This collider is about 27 kilometers long.
Yeah, we
The
talked about
so
that in our physics class.
Yeah.
yeah, so these bunches actually pass through each other as they go through around one set of bunches going in one direction and the other set of bunches going in the opposite direction in the ring. And when they pass through each other, some number of the protons collide with each other. And those collisions are what we're interested in looking at.
But
Is it a relatively
yeah.
small amount?
Well, let's see, the number of collisions,
Yeah.
uh, they're, hap they're happening at the rate of about a billion collisions a second.
Wow.
Oh, wow.
Okay. Also, sorry, a quick middle question here. So you said that they're pretty much they just go in opposite directions, correct? But
Right.
I thought that the beam that was shot out of the LHC, like it goes in many, 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 many circles, and then finally then collides with the opposing particles. Or is that not correct? Or does it just
Well, so what happens is I think you're referring to the acceleration of the particle in the early stage. When the beam is
maybe?
injected into the LHC,
Yeah.
the beam is traveling at about around 15% of its maximum energy. So the first thing we do is we insert the protons in, and then we accelerate them inside the Large Hadron Collider. It's an
Okay.
accelerator as well as a collider, and we accelerate them to then their maximum energy. And at that point, when they actually have gotten accelerated, we then bring them into collision. And then have the collisions taking place right at the center of the detectors that are the down in the LHC itself. So once you actually have them stored, as we say, and in collision, then they remain in collision for typically a border about anywhere from about 5 to 10 hours,
Oh,
and
okay.
and then we dump the beam, and we actually start again with a new beam, a fresh set of protons. And the reason we do that is that as the protons circulate, some number of them are actually every time they turn around in that 27 kilometers, you lose some number of them.
Mm-hmm.
The And you lose some number because of the collisions themselves that are taking place. The
Oh,
so there's a kind of a lifetime for the beam, which is of order around 10 to 15 hours. The
And this process of putting the beam colliding, new beam colliding, new beam colliding, it just takes. How long does it approximately take to find, for example, the Higgs boson? Like, did it take you years, months,
so it took us
weeks?
a so it took us about 2.5 years of collecting data.
Wow,
hmm.
wow, that's okay. Just repeated protons crashing into each other,
Yep,
just
just
trying to find
collecting.
some other particle, pretty
That's right.
much, right?
Just
Okay.
collecting all the data and then sifting through it and looking for, the very specific signatures, the very specific kinds of events that would signal that a Higgs boson was produced and then decayed.
Were you
Oh.
seeing a lot of variance in the results? Or was it relatively the same thing happening over and over again?
Well, so this is a bit of a needle in the haystack problem because I talked about the fact that there are about a billion collisions a second taking place. Well, a Higgs boson is produced maybe once every half an hour.
Oh,
And
okay.
so, and
Okay.
so if you were to think about that, well, half an hour is, it's the a order of around 10 to the 4 seconds. And if you're producing a billion collisions, 10 to the 9, that means that you actually, for every Higgs boson, you also have about another 10 to the 13 collisions,
Oh,
Oh,
wow.
wow.
right?
Okay.
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 So that's a needle in the haystack problem. We have to
Yeah.
pull out the Higgs boson from about 1 in 10 to the 12, 10 to the 13 collisions.
Wow, that
That's
And
sounds like
incredible.
very hard work.
so that's a challenge.
Mm,
And
Yeah.
and that's what made it, that's what took so long, because they're rare to begin with. And then we have to convince ourselves that when we're doing this, we've never done it before, right? No one is telling us how we're
mm,
supposed to do it. We have to sort of
Yeah.
find our own way, and we have to convince ourselves and others that, that we finally come to a class of events, a small number of events out of this huge number that we think are Higgs bosons. We have to convince people that we know how many of those candidate events are fake, and therefore how many are real.
mm.
And
Hmm.
and so that is where most of the work goes into in the data analysis. It's convincing yourself, and this is where the math comes in, right? You're doing
Yeah.
deep, heavy statistics on these events, and you're trying to actually measure something you've never measured before. The so uh,
Right.
the you know the the way that we're able to sort of convince ourselves that we haven't screwed up in some way is that there was another collaboration doing exactly the same thing that was doing it, and we had kind of firewalls between ourselves, that we did not know what was going on the other side of the ring, and they didn't know what was going on in our experiment.
Hmm.
And the so that when we found it, when my collaboration decided that we had really discovered it, um, it was at that point the lab director said, okay, so what's the other collaboration doing? And they had already come to the same decision. So when we actually presented the results back on July 4th, 2012, uh, in fact, both collaborations presented their results one after the other. And they were
Oh.
exactly consistent. Statistically speaking, the results were very compatible, um,
Oh, that's amazing.
and people, there's a whole movie about this called Particle Fever. That
Oh, there's a movie on this.
Yeah, and that's worth actually watching.
Okay, okay, and it's called Particle Fever.
That's right.
Wow, that's pretty interesting. Okay, so it's already 32 minutes, but I really do want to answer the. I want you to answer this final question, and because you were my professor in this course, I think it's suitable that you answer the question to what do you think about like dark matter. Okay. I'm not gonna lie. Originally, I was gonna ask about dark energy, but now I think because you're mainly focusing on particle physics, uh, I think dark matter would be the more appropriate question. So, what are your views on dark matter?
I think dark matter exists. It's really
Hmm.
hard to understand what we observe without having something that we nowadays talk about as dark matter. I think it's most likely a particle, but it could be
Okay.
something else.
Hmm.
That's more of a hunch than
If
based
it's not a
on.
particle, what else would it be? Would it be like some sort of energy, or would it? But then that would be dark energy.
Eh,
No, it wouldn't be energy. Sorry. So just a question:
no.
if it's not a particle, what else would it be?
Well, you and I talked about this a lot in this seminar class. What are the
Yeah.
possible models for dark matter?
Mm-hmm.
And and there are models which you remember we talked about the possibility that, well, what we're really observing is actually gravity changing in a way that we don't really understand.
Mm.
And you could say, well, is that really dark matter or not? Well, it's not clear. The it's also possible that dark matter is not a particle, but it's a field. The particles and fields or waves are in many cases you can't separate them. There's duality, the
Mm-hmm.
wave particle duality we call it in quantum mechanics. So maybe it's more properly seen as a field, but I think that it's actually a particle. It just makes more sense. Uh, all the data we have you have to, it just points in that direction. But the fact that you have all these fingers pointing in the same direction does not make it so until you really have observed it.
Right.
That's true.
Are there any definitive properties that we know about dark matter today?
Probably the most definitive is that it causes gravitational interactions. It actually attracts things that are massive. And that's really what makes the evidence for dark matter so strong. Galaxies rotate faster than they're supposed to. You look at the uh, there's an effect that where light is bent by gravity, and so you actually
Gravitational lensing.
exactly. And so gravitational lensing
Yeah.
the amount we observe is way too much for to be explained by the ordinary matter in our universe.
Oh,
And
Mm.
finally, the one that probably the strongest piece of evidence is that if you look at the nature of the early universe, studying the cosmic microwave background radiation, the patterns, the fluctuations in from one point to another of that radiation is best explained by a theory that incorporates a particle form of dark matter. The So all those sorts of things hang together very well. The fly in the ointment is that we haven't actually observed any particle that could be a dark matter
That's true.
candidate.
Long time.
Yeah, we've been,
Hopefully, we will find it soon.
hopefully we'll find it soon. But this is actually the nature of doing science, right? We're actually trying to discover things.
That's true. Exactly. Exactly. Okay, so we're 36 minutes in. I think you've been a fantastic guest. Thank you so much for joining us
yeah,
You're
today.
welcome.
super
My
interesting.
pleasure.
Yeah, it was awesome talking to you. Um, I guess, yeah, we've gone through all of our questions, I think.
Yeah, pretty much. And once again, we'd just like to thank you, Dr. Sinervo, for joining us today on this podcast.
It's been a pleasure.
Uh, Thank you so
You're
much.
very welcome.
Thank you so much. And now I think we'll be signing off. I'm Ray, and
Parker.
Uh,
we will see you soon.
All right.